Welcome to the most important topic in this module, that is the Pagerank algorithm. It was proposed by Larry Page in 1998 and it has marked a big difference in the web analysis techniques. PageRank has emerged as the dominant link analysis model because it's query independent, so it can be used for any type of queries and it's very effective towards combating spamming. So this was a huge reason behind the initial success of Google. PageRank relies on a democratic nature of the web. That is, the more people are voting for something, the better that thing is. But it also takes care of the uncontrolled nature of the web. That is, anyone can link to anything. So PageRank interprets a hyperlink as a vote that a page X has in page Y. So if we have a page X and that is having a hyperlink to another page Y, then basically X is showing its trust in page Y and is sharing its audience with Y. But it's not just the number of voting, just like the end links that we saw for the other prestige techniques. PageRank is particularly cautious at the number of outlinks a node is having. So what it basically does is that it assigns weights of importance to a vote that is being given. Like if we have another node over here that is also voting for Y, let's call this one Z. So these two votes are going to have different weights. Now the weights depends on two things. That is, what is the original weight of a node that is voting for another node? And secondly, how many other nodes are they voting for? So if Z has got a low prestige value, its vote is also going to be considered of a low weight. It's the same like if an unknown person is recommending a product. But if X is popular, then more people are going to listen to X and therefore the weight of its vote is going to get higher. But in another scenario, even if X has got high weight, but F happens to be voting for everyone, then that also is going to reduce the weight of each vote considerably because whatever X has as its prestige is going to be divided among multiple other nodes. So it's a weighted voting mechanism where it evaluates who is voting, what is their prestige, and how much they are voting. So it does operate on the end links, but the most important thing over here is that instead of considering all the votes to be equal, it deals with them differently. When a page of high prestige is pointing towards I, it's more important than a page of lower prestige pointing towards I. So the prestige of the node that is voting for I is going to count towards the prestige of I. If more nodes are pointing towards a node, that is going to help it get better prestige value. Now this is the algorithm that was originally proposed for calculating the page rank or the prestige of a page or a resource on the World Wide Web. Considering a graph to have vertices and edges, the prestige of any page I is equal to the prestige of all the pages that are pointing towards A, that is having their outlinks directed towards I, divided by the total number of outlinks that they are having. So if we calculate this, it's going to give us a prestige value for the node I, and the process is going to be repeated for all the nodes. Now if we consider a very simple graph that is having a node A, B, and C. A and B are having a bidirectional edge while B is pointing towards C. Now in this case, to calculate the prestige or the PageRank score for the page A is going to be equal to the prestige of the node B, because B is the one that is having its outlink directed towards A. So what is the prestige of B? And this is where the weighted voting thing comes into play, because whatever the weight of B is, that is how much importance its vote is going to get. And then we are dividing it by the number of votes that B is having. So B is voting for both A and C, so therefore we have to divide the prestige of B by 2. In other words, if B has got its own page rank of 3, that is going to give a page rank of 3 by 2 or 1.5 to page A. Now using this new value of A, we can recalculate the value of B. So the page rank of B is going to be the page rank of A, and only A is pointing towards B, so we do not have any more edges to sum up all their weights, so it will be A, and A is not voting for anyone else. So all its prestige is going to contribute towards the vote that it is casting for B. So whatever its value is, that is 1.5, is all being used to cast a vote for B. So B is also going to have its value reduced from 3 to 1.5. The same way we can calculate the weight for C, and that would be just for one iteration, and then you'll keep on moving from one iteration to the, and a point will come when these values will get stable, and that would be our final values for a network. The process can also be represented as Pi minus 1 is equal to AT, where A is the matrix that is going to have all the values of who is voting for whom and how much they are voting, and this is going to be the weights that we have from the previous iteration. So if we define P0 to have the initial weights for all the pages, let's say we want them to be 2, 2 and 2, so we'll use these weights as P0 and multiply it with A transpose, and that is going to give us P1, and then using P1 in the equation is going to give us P2, and the process is going to continue, and the difference between Pi and Pi minus 1 is going to get smaller and smaller until we reaches a point where it's negligible, and that's where we are going to stop. For that we can use a stopping criteria like tolerance, which can be defined as, let's say, 0.1, which means that if the difference between P of I plus 1 and P of I is smaller than 0.1, then you should stop the algorithm, because we may not want the accuracy beyond this point. So those values are good enough for us, and that would be considered as the stopping criteria for the algorithm. Now this is the matrix that we were talking about that is going to have the network structure, and this matrix is going to be static because it represents the whole structure of the network, which is not expected to change anytime soon. So having this structure, if we start up with any initial values as the page rank of these pages, then based on the Markov chain, the values are going to improve iteration by iteration. So how are we going to populate this matrix with the values? So for that, if there is an edge from one node to another, it's going to be 1 over the total number of votes that that node is having. That is the total number of outlinks. If you do not have an edge between the two nodes, then that is going to be 0. The sum of all the votes that a node is having is going to be 1. So using this approach, we can fill up the values in this matrix, and that is going to define the structure of the matrix for us, so that we can continue with this formula and keep on identifying new values each iteration. So following the Markov chain, there is a stationary probability distribution that the model can achieve when it keeps on moving one iteration after another to reach that stationary probability state. Now what we consider a stationary probability state is the one that if all the pages have got their page rank scores of, let's say, 2.5, 2 and 3.1, so even if we go to the next iteration, the values are going to stay the same, or the change is going to be so small, as we said, that we do not require accuracy beyond that point. And if we keep on moving from one iteration after another, the values are barely moving. So that's what we consider the stationary probability distribution, after which the values are not going to move. Now the interesting thing about this is that whatever the starting point we may have, we are going to converge to the same stationary probability distribution. So if we give these initial values, we are still going to end up over here iteration by iteration. So basically it does not matter what we have as the initial values of page rank for the pages, they are going to settle on their original values, which would represent the stationary state. However, the only difference is that if your initial values are good enough, that is going to take fewer iterations to converge to the actual solution, but anyway, that is going to happen. And that is what we call the final state, that whatever the vector is that is having the page ranks for all the pages, if we keep on multiplying it with the A transpose, we are going to get the same final state vector. And if we keep on repeating the process, it's still giving us the same vector, which means that we should stop over here. And as I said earlier, in some cases this change is going to be so small that that would also indicate that it's better to stop at this point. This vector can be considered as a principal eigenvector for the matrix AT when the eigenvalues are 1. Please do keep in mind that PageRank has been evolved over the past 2 decades and different versions of PageRanks are available. Researchers are continuously trying to improve the algorithm by making PageRank more efficient and adding more parameters to it, and therefore there are different versions of PageRank available. So if this is our network, so this is how A is going to be represented. Now this is for the node 1, this is for the node 2, 3, 4, 5, and 6. So 1 is not pointing towards itself, so it's 0. 1 is having an outlink to the node 2 and to the node 3. So it's having 1 vote for the node 2 and 1 for the node 3, and in total it's casting 2 votes, so therefore that is being divided by 2. Because we said over here that the total should be equal to 1. So if someone is casting 3 votes, so that is going to divide it into 3 parts. So that is going to give us 1 vote divided by 3, or the value of its vote is going to drop to 1 by 3. And it's not voting for the node 4, 5, and 6. Node 2 is voting for node 1 and node 3 and is not voting for any other node, so its vote is divided by 2. Because whatever the value of its vote is, each one of them is going to receive half of that value. Node 3 is only voting for node 2, so whatever the value of 3 is, 2 is going to receive all of it, so therefore it's 1 by 1, and we have a 1 over here, and 3 is not voting for any of the other nodes. Node 4 is voting for 3, 5, and 6, and therefore whatever the value of its vote is, that is going to be divided into 3 pieces. Each one of 3, 5, and 6 is going to receive one of the 3 parts. 5 is not voting for anything, so the whole row is filled with zeros, and 6 is voting for the node 4 and 5, so therefore whatever the value of its vote is, that is divided by 2. So now if we add up all these rows, we are going to get 1. The value of a vote of node 1 is divided into half, and it's being provided to 2 nodes, so it sums up to 1. The 2 votes that node 2 is casting are having half weights and therefore sums up to 1, and therefore node 3 is casting only 1 vote, all its value, so that is being 1, and the same way for all the other nodes. So this is our A matrix. So this is going to give us our A matrix. Now an important thing to consider is that we have this row 5 that is not doing much and is having only zeros. So in order to address this problem, there are 2 types of solutions. One of them is to remove this row completely, and that is going to affect the shape or matrix. Alternately, what we can do is that voting not for anyone also means to be voting for everyone. So if we replace all the zeros with 1 by 6, which means that since there are a total of 6 nodes, that this node is voting for everyone, so whatever the prestige 5 is having is going to be equally distributed among all these nodes, and therefore their ranking is not going to be affected. Their page rank values will change, but the ranking is not going to be affected. So let's just go with the second solution. So now we are all ready to continue. We have our matrix A having the distribution of votes that is depicted from this network, and this is the formula that is going to help us identify the prestige values. So in the next lecture, we are going to calculate page rank for this network using the formula originally provided. So stay tuned. Welcome again. This lecture is of particular importance because in this lecture, we are going to solve PageRank algorithm for the sample network we have got over here. So just to give you a quick recap, in the last lecture, we generated this matrix A from this network, and we resolved the issue of having a complete row with zeros. For that, we replace the whole row with 1 by 6. So let's just continue with how it's going to be solved. This is the formula that is being provided to us in the initial PageRank algorithm, that using the PageRank values of all the pages in the previous iteration, multiplying it with A transpose is going to give us the PageRank values for the current iteration, and then putting them back in this equation is going to give us the values for the next iteration. So the process can continue, and in each iteration the values are going to get refined. But the problem is we need to have a starting point. So for that, we have assumed that P0 is going to be our initialization, and we have assigned a page rank of 1 to page 1, 2 to page 2, 3 to page 3, 4 to page 4, 5 to 5, and 6 to 6. As we said earlier, these initial values do not matter for a high number of iterations, as the values are always going to arrange in the order that they should be using the PageRank algorithm. So next we have taken this matrix A that has this issue resolved, and we have taken a transpose of it. Now for those of you who do not remember what a transpose is, so we are converting the rows into columns. And doing it for all the rows, we have got the transpose of A, and now we are ready to continue with this multiplication, and that is going to give us our new PageRank or prestige values. So using this equation, we have P0 using these assumed values of PageRank for all the pages. We have got A transpose from the network structure, and multiplying the two is going to give us the PageRank values for the first iteration. So if you multiply this matrix with this vector, these are the modified PageRank values for all the pages. So we initially assigned a PageRank of 1 to node 1, and it's being modified to 1.833. Similarly, we assigned this a PageRank of 2 that has been gone up to 4.33, and all the values are adjusted accordingly. To this one, we have assigned a higher value, and it has gone down to 2.1. So the values are going to adjust by themselves. In the next iteration, if we provide P1 and multiply it with A transpose, that is going to give us the PageRank values of all these nodes for the second iteration. So over here we are repeating the values using all these PageRank values that we have got from the first iteration and multiplying them with a matrix that is not going to change, and this has given us the values for P2. So the values keeps on changing, and the same way using the values from P2 is going to give us the values for the third iteration. If we keep on continuing this, so skipping few iterations in the middle, if we look at P9 iteration, that is going to use P8 and is going to give us the values for P9. So looking into the values of this iteration, we have got this one as the highest value, so this is our rank 1. Then we have got 6 as the second highest value, so this is our rank 2nd. Then this is the third highest value, having rank 3. Then we have 5 at rank 4. Then we have this one as the 4th highest value. Then this one is the 5th highest value, and then we have this one to be the lowest value. So this is the ranking that the PageRank algorithm has suggested. Again, considering that particular scenario of a query, if the query is given and all these pages are relevant to the query, they should be presented in this order. That is, first we will have page 2, then page 3, then 1, then 5, 4, and then 6. So these are the nodes, and these are their respective PageRank scores. According to this ordering, node 2 should be the first one, node 3 should be the second one, and so on. So these are the values that we just saw in the previous experiment, and this is the order that is being generated. Now let's just conduct another experiment and compare the values. In this experiment, we have reshuffled the values. Like over here, we have the initial value for page 1 as 1, but in the next experiment, we have assigned a score of 4 to page 1, to node 1, and 3 to node 2. In this way, all the values are reshuffled, skipping few iterations in the middle, and these are the scores from the 9th iteration. So node 1 has got the PageRank of 4.55, so if you compare it with this one, the values are almost the same. Node 2 has got a score of 9.24, and over here the values are again very much similar, and over here we have got the score of 6.9, which is again quite close to 6.8, and this way the values are quite similar and the ranking is exactly the same as it was suggested in experiment 1. So this is the beauty of the PageRank algorithm, that whatever your starting point is, it is always going to converge to that stationary distribution, after which it's hardly going to make any change. We are only considering the first 9 iterations. If you go to 100 and 200 iterations, the values are going to get even further closer. In the third experiment, we are using a completely different range of values. We are assigning all the nodes to have the initial page rank of 100. Now with this one, the values are changed because we have completely taken them into a different set of values. But you would observe that the ranking is not modified. As you can see, this is the highest value. Page 2 has got the rank of 1. Page 3 has got the rank of 2 as the second highest value. Page 1 has got the rank of 3 as the third highest value. Then we have page 5 with the rank 4. 4 happens to be at rank 5 and 6 is at rank 6. So the ranking is still not affected and the values are modified because we have a different set of values, and now the values have rearranged themselves in that particular range so that we can get exactly the same order as ranking of these nodes. Now let's just look at another very exciting aspect of the PageRank algorithm. Let's say we assign values to all the nodes in such a way that they all sum up to 1. Over here we are exactly dividing them by 6, so everyone is getting the 1 by 6th part equally. So whatever the arrangement may be, but if all the page ranks are summing up to 1, then after every iteration they are going to sum up to 1. And you can verify this, it's going to be very close to 1, and this is now even better because if we look over here, we know that node 2 has got higher page rank than node 3 or node 4, but we do not know how much this difference is because the values are not in any particular scale. So we do not know whether this difference of roughly 65 score is good or bad. But if we bring all the values to a scale of 1, now we can see that this score is 40% of all the scores that we have in the network. This one is getting almost 20% of all the scores of the network. So in this way, we can see that what is the proportion of the page rank of a particular page considering the whole network to have a page rank of 1. In the next lecture, we are going to evaluate page rank for the same network using a slightly modified algorithm that was presented later on. So keep watching. Welcome again. In this lecture, we are going to solve another page rank formula for evaluating the ranks of nodes in a network. This formula was presented in a later on research paper that has modified the original PageRank algorithm. Now, if you may recall, this was what we had in the original PageRank algorithm. And this has been introduced as an improvement on the PageRank scores of all the nodes. D is called the damping factor that is going to be constant throughout the experiment. Its value can be anything from 0 to 1. However, in the same paper, they have suggested that a value of 0.75 or 0.8 is highly recommended. We can also represent it in the form of a matrix as this, where A transpose is going to be multiplied with P. This is what we were originally doing, but after that we'll have to multiply it with the scalar value of D, add in this value to it, and that is going to give us our P for the current iteration, and the process can be repeated for any number of iterations. So in case you want to solve it through the matrix, so this is how it can be evaluated. So now using this formula, let's just evaluate PageRank for our sample network. So this is the network that we are going to use, and this is the formula that we have. Again, we need to assign the initial page ranks to all the pages, and we have used the same values, that is 1, 2, 3, 4, 5, and 6 for all the nodes. So node 6 has got the page rank of 6, node 5 has got the page rank of 5, and accordingly. So using this formula, if we have to calculate the new page rank for page 1 in iteration 1, it's going to be 1 minus 0.8, as we decided damping factor to be 0.8, plus 0.8 into 2 by 2. Now this is what we were doing originally in the previous algorithm also, that 1 is getting an in link from 2, and 2 has got its page rank of 2, so we have got 2 in the numerator, and then the node 2 is having 2 outlinks, so whatever its page rank is, which is 2, is going to be divided by 2, so that is going to give us 1, and if we solve this, this is going to give us a value of 1. So the page rank of page 1 is not affected in the first iteration. The page rank of page 2 can again be evaluated having this part as constant. We have this part the same way we had in the previous algorithm, where node 2 is having in link from node 1, and node 1 has got its page rank of 1, and since node 1 is having 2 outlinks, so its prestige of 1 is going to be equally distributed between both, so 2 is getting half of its prestige, that is 1, so that becomes 1 by 2. The prestige of 3 is 3 as we originally decided, and 3 is not having any other outlinks. 3 is only having its outlink to 2, so 2 is going to receive all the prestige from 3, and that is going to be 3 by 1, because there is only one outlink and that is coming towards 2. So that is going to modify the page rank score of node 2 from 2 to 3. The same way, using these values as we saw originally in the previous algorithm, but this part is what we are going to have each time, and that is going to give us a value of 2.86 for the node 3. So this one is going down towards 2.86. Node 4 has got its value reduced from 4 to 2.6, and the same way node 5 and 6 have got their values modified. So after the first iteration, we have the ranking as 5, 2, 3, 4, 1, and 6. Moving on to the next iteration, we are using the values of page rank from the previous iteration and using them to calculate the new page rank values. In this iteration, the page rank of 1 has gone up from 1 to 1.4. The page rank of node 2 has gone up from 3 to 3.05, and same way all the other values are being modified. So according to these scores, after the second iteration, the ranking of all the nodes based on their current page ranking is 2, 3, 1, 5, 4, 6. So this is exactly what we had after the 9th iteration in the original one. Moving on further iterations, as you already know that this is the original arrangement, this may not be affected in the coming iterations also, but the values are going to get refined to their stationary distribution. This is another improvement on the PageRank algorithm we just saw, which has introduced this part into the PageRank formula, and there is 1 by n, where n is the total number of nodes. If we expand this part, can also be represented like this, where these are the page ranks of all the pages and the number of their outlinks are in the denominator. So let's just solve it for our sample network using this formula. So this is the formula that we have got. This is our network, and we again are starting with the initial page rank of node 1 as 1, page rank of node 2 as 2, 3, 4, 5, and 6 accordingly. So now the only part that is being modified in this formula is that 1 minus 0.8, where d is the damping factor, and we are keeping the same value for it, there is 0.8. We have to divide this with a constant 6. So this whole part is constant, which was previously giving us 0.2, and now it's going to give us a constant of 0.033. So we have to keep this value and keep on adding this value to all the scores. This part is pretty much the same, and after the first iteration we have got the ranking of the nodes as node 5 being the first one, then node 2, 3, 4, then 1, and then 6. If we move on to the next iteration using the values from the previous iteration, the values are being modified. The prestige of node 1 went down from 1 to 0.83 in iteration 1, and it has again gone up in iteration 2 to 1.14, and all the values are modified accordingly, and as you can see, this is our final ranking for all the nodes in the network. So these were some of the modifications that were later introduced on the PageRank algorithm, and in the next few lectures we are going to implement this through the code also. So keep watching.